Okay, hi. So in this video, we're just going to go through a probability example. We have published a PDF that goes over some common errors we see in probability questions, and in that document is an example. So this is just the video walkthrough of that example. Yeah, so let's just give the question, and then we'll solve it a couple of different ways. Okay, so the question we're looking at is we're asked to consider an experiment of flipping a fair coin 5 times, where the coin flips are independent of one another. What is the probability that I get at least 4 heads? So in this class, the first thing that we should be doing when seeing a probability question is defining a sample space. Oftentimes students will ask why do I need to define a sample space? Why can't I just write the probabilities and then get my correct final answer? And while you can do that if the purpose was to simply get the correct final answer, in this class that is not the case. Getting the correct answer is one part of the experience. The rest of the experience is ensuring you can write up a solution that is appealing to someone who's reading it. This is a proof-based class, so you want to be able to come up with some sort of solution, justification / proof that is understandable for someone. So the sample space is doing just that. It is telling the reader that, hey, this is exactly what my outcomes will look like. I'm defining a structure for all of my outcomes, and this is what I'll be referring to as I go forward in my solution. So that's the purpose of it. So there's a couple of different ways we can define the sample space. In fact, for basically all questions, there will be multiple ways of defining a sample space. So you can choose whatever is convenient for you. But let me start by defining one such sample space. So here's an example of such a sample space. I'm saying that my sample space omega consists of this 5-character sequence or string where each character is either an H or a T. And yes, omega will consist of all such strings of that form. This is a fine sample space. We can make it even more complete by adding on this extra wording. So to tack onto it, I can say where alpha I denotes the result of the ith flip. And this is a very, very good definition of a sample space. And it's not very good just because I wrote it and I'm very good. No, I'm joking. Not because of that. It's very good because I am able to take some element of my outcome space and look at it, and I know pretty much exactly what happened throughout the experiment. For example, with this definition of omega, I know that this HHTHT is a member of omega. But more than that, just by looking at this, I pretty much know exactly what happened in my coin flips. The first flip was a heads, the second flip was a heads, third was a tails, heads and tails, so on and so forth. And the reason why I say it's very good is because this gives us a lot of information to work with. We've reduced the experiment, the entire aspect of the experiment, all down to a single string. So this is one such example of a probability space, sample space. So after defining a sample space, there are potentially two things that could be helpful. First is a question of uniformity. What it means to be uniform is that each outcome has the same probability of occurring, the same likelihood of occurring. And in this case, since we're dealing with a fair coin, the probability of us seeing one such sequence of heads and tails is going to be no more or less likely than us seeing something else. So all of these outcomes are equally likely to occur. So in this case, our sample space omega is uniform. The second thing, which you will sometimes use, it's usually dependent on whether or not omega is uniform, is compute the cardinality of your outcome space. And I'll touch on why this is important right now. When omega is uniform, This, by definition, means that for all outcomes in our outcome space, the probability of that outcome is 1 over the cardinality of the sample space. So by having the cardinality, we can use this fact pretty easily. So in this case, what is the cardinality? It's going to be 2 to the 5 or 32. And the reason for this is alpha 1 can either be heads or tails. There's 2 options. Alpha 2, heads or tails, 2 options. Just use the multiplication rule, and we have 32. Okay, so we've done a lot of setup, but we really haven't solved this, like what is the probability I get at least 4 heads. I've just set up a lot of stuff. So with probability questions, we have this notion of events. Events are a subset of outcomes. And it's nice to have events being defined, so that way we can just like simplify our writing a lot. And in probability, they pretty much give you an event. Like I can just define an event to be the event that I get at least 4 heads, and life will be a lot simpler. So let's just do that. Yeah, my handwriting's a little wavy, but whatever. Okay, so then what we're solving for really is the probability of E now. Okay, so what does it mean to get at least 4 heads? If I'm flipping a coin 5 times, I can either get, to satisfy this, I can either get 4 heads, because 4 is at least 4, or I can get 5 heads, because 5 is at least 4, but nothing else. I can't get 6 or 7 heads because I'm only flipping it 5 times. So let's just define events for getting exactly 4 heads and exactly 5 heads, and then maybe we can rewrite the probability. Okay, so I've defined 2 more events. E4 is the event I get exactly 4 heads. E5 is the event I get exactly 5 heads. So if I get at least 4 heads, one of these 2 must have occurred. The outcome in the at least 4 heads event must be also a part of either E4 or E5. More importantly, E4 and E5 are disjoint because exactly 4 heads, exactly 5 heads, nothing is in their intersection. And together they describe E. All of this is to say that using the fact that they're disjoint and that they together describe E, we can rewrite this probability as follows. And the reason we're doing this is just because it's easier to work with exactly instead of at least. Okay, so let's compute the probability of E4 first. So how are we going to do this? I'm not really sure. No, I'm joking. It's too late. Too late at night. Okay, we'll use the fact that omega is uniform. The reason why this is such a helpful thing to have is when omega is uniform, we can use the fact that the probability of an event E4 is equal to the cardinality of E4 divided by the cardinality of omega. This follows from the fact that each outcome has the probability 1 over omega of happening. And so since we'll just sum up all of the probabilities for all the outcomes that are in E4, and we get this equation. Well, we have the denominator already. So now it's just a matter of computing the cardinality of E4. So this is where set theory comes into play in the world of probability. All of the skills that you learned in the counting unit are going to manifest themselves here. So what is E4? E4... What is E4? The first move I play in chess. Am I really going to keep that in the video? Probably. E4 is the set of events, the set of outcomes with exactly 4 heads. So I could like start writing them out. Heads, 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 tails, heads, 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 tails, heads, and maybe this would take a really long time. Maybe it would. In this case it doesn't, but for the sake of example, we're just going to say that it does take a long time to write out. So what happens when we're trying to find the cardinality of a set and it would take forever to write out? Well, we construct a counting procedure. So let's do that. Well, I want 4 of my alpha i's to be heads, so I will simply choose 4 of my alpha i's to be heads. Then I will assign the heads to the alpha I that I just chose from before, and then whatever is left over, the last alpha that I didn't touch, I will give it the value t, tails. So how many ways are there to perform this procedure? Step 1, 5 choose 4. These 5 distinct alphas, we're choosing 4 of them. Assigning heads can be done in one way, tails one way. So by multiplication rule, we have that the cardinality of E4 is 5 choose 4 times 1, which is equal to 5. So that means the probability of E4 is 5 over 32. Cool, so now let's compute the probability of E5. And once again, we'll use this uniformity concept to just, decompose this a little bit. All we need to do is compute the cardinality of E5. Dude, I had such a nice piece of chalk, and then I lost it. And I don't feel like using my new chalk. So I'm using like this little nub, and it's so hard to write with. Anyway, what is E5? E5 is the event that I get exactly 5 heads. So, similar to before, we will construct a counting procedure. No, we won't construct a counting procedure. Because as I was mentioning here, like, writing out the elements of E4 might take a really long time, so it's best to construct a counting procedure. But if we were to write out the elements of E5, there's only one element in E5. The event that we get 5 heads, this is the only such outcome of that form. So we can just say that the cardinality of E5 is 1 and save a bit of time. I mean, you could construct a counting procedure, choose 5 alpha I to be heads, assign H to them, assign T to the rest, but there is no rest. You would get 5 choose 5 times 1 times 1, which is equal to 1. So the probability of E5 is 1 over 32. And so finally we can compute the probability of E. And there we go. We have the answer of 6 over 32. That's not all. We're going to solve this question one more time. I mentioned at the beginning that we could define our sample space in many different ways. This is one such method, and we ended up getting a uniform probability space. Now we'll see what happens when we define it in a different way and get a non-uniform probability space. Oh, this chalk's on its last living breaths. Alright, so before we get into this, I realize I've been saying sample space, outcome space, and probability space somewhat interchangeably. I apologize for the multiple different vocabulary to use to denote the same term. It's just, there are so many ways to describe it. So if I say any one of those, in this context, they will all mean the same thing. So here's a new sample space. This is going to be the set of ordered pairs x, y, where x is an integer in the range 0 to 5 inclusive. Let me just make this a little bit more clear. And y is equal to 5 minus x. And I'm letting x denote the number of heads I got in my experiment, and y is the number of tails. So for example, maybe I flipped my coin 5 times and I got tails, tails, heads, tails, heads. This would correspond to the ordered pair 2, 3, and sure enough, by definition, this is in my outcome space. So in this sense, omega is a valid sample space, right? Because whatever I do up here, like such an ordered pair will always appear in omega. However, it's not my favorite sample space. I think the first sample space was better because with the first sample space, we were able to look at an outcome and gain a lot of information as to what happened in the experiment. With this, if I just extracted 2, 3 from omega, then I don't really know what happened in the experiment. I could have gotten T, T, H, T, H, but I could have also gotten T, H, H, T, T. Or many other possibilities. So there's a little bit more unknown to us. Doesn't matter. Maybe it's not important. So it's still, a viable outcome space. However, this sample space, dude, I'm using all of the words interchangeably. This sample space is not uniform. And a very quick explanation of why that's the case is we can see that already there are multiple sequences that will yield this 2, 3. But if I think about the pair 5, 0 in omega, this can only be, this is only produced by getting heads, 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 heads. Right? So already we're seeing that this outcome 5, 0 is probably going to be a lot less likely than say 2, 3. So we say it is not uniform. So that doesn't mean that we just give up on the problem. It is actually still solvable using this, this outcome space. So we'll solve it. When dealing with a non-uniform sample space, we can't really use that fraction formula anymore with cardinality of omega in the denominator because, well, it's not uniform. We can, however, leverage independence if we know that independence is available to us. In this case, we know that the coin flips are independent of one another, so we can use that fact. If we didn't know independence, then we probably shouldn't use it. In fact, you shouldn't use it. So we'll use independence. Recall that independence means that if A and B are independent, then the probability of their intersection equals the product of their individual probabilities, and the converse holds as well. So let's just take a look at an arbitrary x, y, which I will actually write as x, 5 minus x, because that is how it's defined. So what is actually the probability of x, 5 minus x? This chalk is so small now. Well, this means I need to see x heads, and I need to see 5 minus x tails. So let's just think of perhaps the simplest sequence of coin flips that could yield x, 5 minus x. And that would be that like my first x flips are heads, followed by 5 minus x tails. And admittedly, like, this is not the actual way the sequences would be written, because here I'm denoting more than 6 coin flips, but just for the sake of example, like the simplest such outcome would be heads followed by tails. So what's the probability of this occurring? Well, this is going to be equal to basically this huge intersection right here, that like my first flip is heads, my second flip is heads, like all of these must occur up to my xth flip being heads, and then the thing right after that, the x flips first, will be tails, all the way up to the, in this case, 5th flip would be tails. And now we can use this notion of independence to say that this is the probability that first is heads times the probability that the second is heads. So we're just using the the independence fact from before. And now this is pretty easy. The probability that my first flip is heads is 1/2, since it's a fair coin. Same with the second flip. And so on up to the xth flip. And then when we get to the x plus first flip, the probability that that's tails is 1/2, because fair coin, all the way up to the fifth flip. So this is going to occur 5 minus x times. And so we can in fact rewrite this as 1/2. We could rewrite it as 1/2 to the power of 5, but I'm in fact going to rewrite it as 1/2 to the x times 1/2 to the 5 minus x. So what is this probability? It is not equal to this probability. It is equal to the probability of us seeing this sequence of coin flips. And this should make sense, because if you were to simplify this, you would get 1/2 to the 5, which is 1/32, which is what we saw earlier on in the first example. But this is not equal to this quantity up here, because we haven't accounted for all such sequences that will produce x comma 5 minus x. However, you can quickly argue to yourself that whatever HT sequence I do to get x comma 5 minus x, like this, suppose that this yields x comma 5 minus x, the probability of us seeing this is still going to be 1/32. Because there's a 1/2 chance I see a heads on the first flip, a 1/2 chance I see tails on the second flip, and so on and so forth. So all of these have the same probability. To find the probability of us seeing this outcome, however, we have to consider all such sequences that yield x comma 5 minus x and multiply 1/32 by that. And we can compute that pretty simply. We have 5 spaces. We need x of them to be heads. The rest will be tails. So we'll choose x of them. So 5 choose x is the amount of heads, tails sequences that will yield x comma 5 minus x. And now we just have to multiply it by the probability we found. And note that this simplification right here between these two, this is by independence. This is not by multiplication rule. It is not by multiplication rule at all. We are able to do this decomposition due to independence. You should not be using multiplication rule as a citation when you're multiplying probabilities. The only real time you'll see multiplication rule in the world of probability is when it goes back to our first example with uniform probability spaces, when we're computing the cardinality of a set. When we're computing the cardinality of a set, it's just like the counting days, where we construct a procedure and then we use multiplication rule on the procedure to get a final answer for the cardinality. When multiplying probabilities, no multiplication rule. Multiplication rule does not tell us we can do it. You will lose points. You will. I'm being very serious. So this is by independence right here. Please, please make sure you understand that. Good. Okay, so we have this like very generic equation right here, and it's very nice because now when we come back to the problem, the probability that I get at least 4 heads, I can just figure out which of these pairs do I need to look at, and then just plug it into there. So let's do that. So then E is going to be my event once again, the event that I get at least 4 heads. By the way I define my sample space, it's just the sum of these two probabilities. The probability I see 4 comma 1, meaning I get exactly 4 heads and exactly 1 tails, plus the probability that I get exactly 5 heads. Just similar to the first example that we did. So now I'll just plug it into here. And now we just simplify. And once again, sure enough, we get the exact same answer. So same problem solved two different ways. If there's anything you should take away from this video, the most important thing is that thing I mentioned about independence. That multiplying probabilities, we can only do that if our events are independent. And when citing what we're doing, you should cite independence, not multiplication rule. Second big takeaway. Sample space can be a lot of different things. However, depending on how you define your sample space, you'll have more or less information to work with. You might have uniformity, you may not have uniformity, and depending on that property, it may change how you solve the question. Those are the biggest takeaways. For me, the biggest takeaway is I need a new piece of chalk because this is gone. Let me see if I can toss it at the camera. Oh gosh, that was really bad. I'll clean that up. All right, it's late. I'm tired. Time to go to bed. Have a good day. Take care.